AP Physics, this is summer lesson number 12 on projectile motion. So, how can vectors be combined? So we talked about this earlier in one dimension. We learned that vectors in the same or opposite directions can be netted. Vectors in other directions can be combined by placing the tip of one vector to the tail of the other. The vectors being added are called component vectors. The vector that results from this is called the resultant vector. So if the two component vectors are shown there, the one moving to the right and the one moving to the a diagonal up to the right, if you add those by placing them tip to tail, then you get a component vector. That's the longer vector that you see there. That's called the resultant. The magnitude of the resultant can be determined by measuring it. So notice there's no way to mathematically combine those two component vectors because they're not moving in the same or opposite direction. So you can combine them by doing it graphically like this, placing them tip to tail, and then measuring the length of the resultant vector. So how can vectors at right angles be combined? Well, most often we will deal with vectors that form right angles, 90-degree angles. Usually the component vectors are placed tail to tail so that the resultant can be seen clearly, then by drawing a parallelogram. So these two groups of vectors are the same. So the two component vectors are shown over there on the left, and you place them tip to tail, and once you do that, you see the longer vector, the resultant. But those two arrows kind of get in the way of each other, so what you often do is place them tail to tail. So those are the same vectors. Remember, you can move a vector around a page as long as it has the same direction and the same length. As long as you don't change those two things, you can move it anywhere on the page. So we took it on the right side, we took the two component vectors and placed them tail to tail. Then we created a parallelogram. In this case, it was a perfect rectangle, but it doesn't always have to be a perfect rectangle. And from that, we got the resultant vector. And you can see how it's drawn there. So you get the same resultant vector. So now let's get into projectile motion. Projectile motion is the motion of an object under the influence of gravity. Once a soccer ball is kicked into the air, the only force acting on it is the gravity pulling it downward. So that's an important fact to remember, that once it leaves your hand, let's say you threw the ball or kicked the ball in the air, once it leaves your foot or your hand, there's no force acting on it to move it upward or to the right. The only force is one that's pulling it straight down. So objects under the influence of gravity form a shape called a parabola, which is a function of a quadratic equation. So projectile motion has three parts. The upward vertical negative acceleration, that is, as you kick a ball in the air, it slows down going up. The downward vertical positive acceleration, it speeds up coming down. And the horizontal or constant velocity going from left to right. So down below, the soccer ball slows as it rises. The soccer ball speeds up as it falls. And this is the one that some students find tricky, is it speeding up or slowing down as it goes from left to right? The soccer ball moves at a constant velocity in the horizontal sideways direction because forces in this direction are balanced. They're zero. In other words, once the ball leaves your foot, there's no force pushing it to the right any longer. If there's no force, that means the forces are balanced. Then that means it's going to be moving at a steady or constant velocity along the ground. Here's a way to think of it. You kick the ball up in the air on a sunny day and the sun is directly overhead. If you were able to look at the ground and watch the shadow of that ball as it flew up and over to the right and came down, the shadow of the ball would be moving at a steady speed. It would not be speeding up or slowing down. It may seem to be doing so. That's an optical illusion. It actually is not speeding up or slowing down if you neglect air resistance, and we always neglect air resistance in these problems. A curve can be represented by the resultant vector of two perpendicular vectors. So the horizontal vectors are the same length because the ball moves sideways or horizontally at a constant velocity, as we just said. So you notice those vectors pointing to the right are all the same length. The vectors going up, well, let's read this. The vertical up and down vectors are long on the bottom because the ball is moving fastest when the ball is thrown upward and just before it hits the ground. The ball gets slower and the lines get shorter near the top. So it slows down as it goes up to the top. That's why the vectors going upward get shorter. And then as it comes down, they start off short. It's coming down slowly, and then it speeds up as it gets closer to the ground, and that's why the vectors get longer. If you took vectors at the same level, let's say at 5 meters above the ground, the ones going up and the ones going down, they would be exactly the same length, because at 5 meters the ball is going the same vertical speed upward as it's going downward when it's coming down. So let's say it's going 7 meters per second going upward. Then if you come over to the same elevation with the ball coming downward, it would be going 7 meters per second going downward. The resultant of the vertical up and down vector and the horizontal sideways vectors are shown in the blue below. So you can see how that formed a resultant the way we did a few slides back. The blue arrows are resultants of the red vectors. Notice how the blue vectors form the curved shape of a parabola. So you can see how it's forming a curved shape there. If you drew all the vectors, it would be a perfect curved or parabolic shape. So let's look at some examples. A ball is punted and stays in the air for 4 seconds. How high did the ball go? So the ball is in the air for 4 seconds. So it spends 2 seconds going up and 2 seconds going down. That's an important thing to remember in these problems. You divide the flight time in half. 2 seconds up, 2 seconds down. Since height is a distance, we can solve it this way. Distance equals acceleration, which is g, in this case, gravitational acceleration, times the time, 2 seconds. So d equals 1/2 at squared, which is 1/2 10 meters per second squared times 2 seconds, and then you square the 2 seconds. That gives you 20 meters. So the ball rose to a height of 20 meters, about the height of a 6-story building. A ball is punted and is moving at 30 meters per second upward when it leaves the punter's foot and travels 60 meters downfield. How long did the ball stay in the air? Well, we know the ball comes to a stop when it gets to its highest point, so its final velocity going up is 0. So the time, so acceleration, now here acceleration is negative 10 meters per second. Why negative? Because we're assuming that the positive direction is going upward. That means acceleration is pulling it down in the negative directions. Remember what we said in the last lesson, that the ball does not have to be moving in the direction of the force or the acceleration. In this case, it's moving upward, but the acceleration is pulling it downward. So the initial velocity off the kicker's foot is 30 meters per second. When it reaches its highest point, it's 0 meters per second. So now we can use the formula acceleration equals final velocity minus initial velocity over time. You have to do some algebra here and solve for time. And we will practice these types of algebraic manipulations. So we see down there on the bottom right, the time equals final velocity minus initial velocity divided by acceleration. So the time is going to equal the negative 30 meters per second over negative 10 meters per second. Again, the final velocity is 0. 0 minus 30 is negative 30. And we said earlier the acceleration is negative as well because it's pulling against the movement of the ball. So the negatives cancel out, so the time is 3 seconds. So the ball spends 3 seconds going up and another 3 seconds coming down for a total of 6 seconds in the air. A ball is punted and is moving 30 meters per second upward when it leaves the punter's foot. The ball travels 60 meters downfield. How high did the ball go? Well, we know from the previous slide that it went up for 3 seconds. So distance equals acceleration times time. And so distance equals 1/2 at squared. And the distance is 1/2 times 10 times 3 squared. That's 45 meters. It went 45 meters in the air. The ball rises to a height of 45 meters, then falls back to Earth 45 meters. A ball is punted and is moving 30 meters per second upward when it leaves the punter's foot. The ball travels 60 meters downfield. What was the ball's horizontal velocity? Again, this is sideways, also known as ground speed. Well, we know that the ball traveled 60 meters downfield in 6 seconds because it stayed in the air for 6 seconds. We don't care about the upward or downward motion in this part of the problem. So the velocity is simply going to be the 60 meters that it traveled downfield, divided by the time that it took it to do that, 6 seconds. So that means it's moving at a steady velocity of 10 meters per second from left to right downfield. In other words, the shadow of that ball on the ground, if the sun is directly overhead, would be moving along the ground at 10 meters per second. All right, so that was a little bit involved, but we will do a lot of practice with projectile motion problems. And again, you'll see a lot of problems during your time in this class, and you will become very good at these.